I've talked about how to check the conditions for linear regression, but we haven't really discussed what to do if the conditions are not met. So there's actually several different options, but one of the simplest ones is just a data transformation to re-express one or more of your variables on a new scale. A lot of times these are called linearizing transformations because the association between the transformed variables may be linear even if the original association is not. And you can sort of figure this out with trial and error, adjust the severity of the transformations by raising or lowering the power. So I have them sort of listed in order here, y squared. Below that would be just y, so that's like y to the first power. Square root of y, that's like y to the 1/2 power. The log of y, sometimes we think of that as like y to the 0 power. 1 over y would be y to the -1 power. So we can just sort of adjust along that ladder. So let's consider an example where we're looking at the relationship between stopping distances in feet for cars traveling at different speeds, and that's in miles per hour. So we want to use the speed to help explain the variance in stopping distance. So at first we would just consider a regular linear model with speed as the explanatory variable and stopping distance as the response. So I'm going to do this in jump with analyze fit y by x. Stopping distance is my y and speed is the x. And I've got the scatter plot there and I can fit a line to it. So maybe already I can see a little bit of a curved pattern here. To see it more clearly, I'm going to plot my residuals. So I'm clicking the red arrow next to linear fit and plot residuals. So we talked about the residual by x plot. Looking at this, I think there's a clear curved pattern here. So it seems like we have a lot of negative residuals here in the middle. So if you have negative residuals, that means that your actual values are lower than the predicted values. In other words, the model is overestimating there. Whereas if we look at the ends, the lowest and the highest speeds, we have a lot of positive residuals. So that means that the points are above the line, right? That the actual values are higher than the predicted values, which means the model would be underestimating. So with the original model, it would overestimate for speeds that are in the middle. So we're talking about like these, but it would underestimate for the highest and the lowest speeds. So on both ends here. We can also see a little bit of a funnel shape where the spread is really small down here on the low end. The points are falling pretty close together, pretty close to the regression line, and the spread is much bigger up here on the high end. So that's an issue too. That funnel shape would indicate that we have non-constant variance. So those are both things that we would like to address with our transformation. So let's start with analyze fit y by x again. So a really common transformation to use is to take the log of the response when we have that sort of sloping up effect. So the way we do this in jump is we right-click on the variable. So I'm going to right-click on stopping distance, and I'm going to click transform. And the first one I'm going to try is a log. This is natural log. It also has log 10. Usually it doesn't make much difference. So I'm going to do the log there, and then I'm going to put that variable in as my response. So I'm using the log of the stopping distance as my response variable and still using speed as my explanatory variable. So we can take a look at this one. We can fit the line. We can also look at the residual plots. And unfortunately, this doesn't really seem better. It kind of has the same problem, just in the other direction. So now we've got positive residuals in the middle, negative residuals on the end. But I wouldn't say that this is any better. It seems like the log transformation is an overcorrection, right? We still have basically the same problem, just in the opposite direction. So we want to find kind of a compromise between the original model and the log. So if we look at the ladder here, first we started off just putting y on the y-axis. Then we tried log of y. Let's kind of split the difference and look at the square root. So I'm going to do one more time, analyze fit y by x. Right-click on my response variable to transform it. But this time I'm going to do the square root and put that in the response box. And this one turns out really beautiful. So we've got a nice straight line. If we plot our residuals, we can see that the curve pattern has gone away. We also have a nice even spread, so it's pretty much even all the way across. We notice that this histogram of the residuals looks pretty bell-shaped, and then we can confirm that with the normal quantile plot or the QQ plot, right? These points are falling really close to the line. So after doing this transformation, it has fixed all of our issues. And luckily that happens sometimes where one transformation can solve more than one of your problems. Other times you kind of have to prioritize. So like linearity is definitely a big deal. That's something that's going to affect your predictions. You might be over or underestimating consistently. For constant variance and normality, we've talked about the consequences of those. So like normality could be less of a big deal, especially if you have a large sample size, just keeping in mind that your prediction intervals are going to have issues. And you may want to go back to that previous video if you have questions about the effects of violating the conditions. But yeah, in this case, it turned out great. The square root fixed both our problems. So now we have linearity, we don't have any curved pattern, and we also have constant variance. So it's very clear here that this is the model that we want to use. So I'm taking this parameter estimates table, and we're going to use that to make our predictions. So if we want to write our regression equation, remember that the response now is the square root of the distance. And besides that, we write everything out the same. So the intercept is 0.918 plus 0.253 and then speed. So for this one, we didn't transform the explanatory variable. We just left it as it was, and it seemed to work out okay. All right, now we're going to use the model to predict stopping distance for a car that's traveling at 25 miles per hour. So we've got a speed of 25. That's what we're going to plug in. And this is going to be a prediction for the square root of distance. So we've got 0.918 plus 0.253, and then I'm plugging in 25 for the speed. And when I do that, I get 7.243. But remember, this is not a prediction for the stopping distance. This is for the square root of the stopping distance. And so if we want to get the actual distance, we're going to have to square both sides. So we'll take that 7.243 squared, and our predicted value would be 52.46. So it's always really important when we go to make our predictions that we remember to undo the transformation and get back to the original scale.